All right, let's have a go here. This is a slight review of what we did as we ended the year in Honors Pre-Calc. So, we had a fundamental question we were looking at, and that question was essentially this. How fast? For example, I'm oversimplifying, but the idea is this. Can we calculate how fast something is going? And for example, let's look at this example right here. Let's suppose we have the graph of something that is moving. Because if it isn't moving, the question of how fast would be pretty simple, wouldn't it? Let's say something is moving, and let's say that thing that is moving is a student, and that student is running. Why would a student be running? Well, they might be running a 100-meter dash. So let's put meters over here and seconds over here. And let's just, for the sake of not getting too bogged down in the physics or reality of it, let's say they start here and they run, and then they reach 100 meters, at which point they no longer run. And let's just say, for the sake of argument, that takes 10 seconds. I know, that's fast. But this is math. Math is freedom. We can make ourselves fast. So, quickly, how fast on average is the student going over this 100 meters? If they go 100 meters in 10 seconds, then their average speed is correct. Good job. But their average speed isn't the same as their speed anywhere. So what I want you to do real quick is answer, where is this student going fastest? You could pause the video and decide, where is the student going fastest and where are they going slowest. Pause the video. Good. You should hopefully have somehow come to the conclusion that this is slowest and this is fastest. How did you come to that conclusion? Well, there's a bunch of ways. Let me throw one piece of reasoning at you, and maybe you had something else that was equally reasonable. Suppose we have a fixed amount of time, like down here. Suppose we go three blocks here. In that fixed amount of time, we've gone this distance. If we take that same fixed amount of time out here, 3 blocks, oh, whoa, look at that. In that same fixed amount of time, they've gone that teeny little distance. So one could reason in that manner that they're going faster here, slower there. Of course, this idea of speed or rate of change is linked to what mathematical concept? Pause the video, see if you remember that. Speed, rate of change. In case you're not pausing the video, I'll say nothing of great importance in the next few seconds, so you could ponder that. The speed, or the rate of change, is connected, of course, to slope. So that we could calculate an average rate of change, which you did. Average rate of change, or in this case, average speed. We'll get into the difference between speed and velocity later, if you haven't already done so in a physics class. So your average rate of change, you can calculate the slope over some interval. For example, the average rate of change for the entire race is 10 meters per second. But your average rate of change over here is more than 10 meters per second. And your average rate of change on this little interval up here is less than 10 meters per second. Which of course brings us to what our fundamental question, which hopefully you remember from the spring, is can we find the instantaneous rate of change or the instantaneous speed? And that of course is the slope at a point. And this idea is fundamental to most of what we'll do in the beginning part of calculus. And of course, to draw that, for example, if we wanted to know the speed exactly halfway, we would draw a tangent line. I'll try to draw a tangent line. Maybe I'll draw one up here. It'll be easier. So if we want to know the speed, right, but how fast they were going, this student incidentally was kind of started out a little bit too strong and lost steam along the way here. Common mistake among young people. We could draw a tangent line. I used no special effects to draw that tangent line. I'm just really that good at it. So that the slope of that tangent line is the same thing mathematically as the slope at a particular point where it touches. We have the corresponding concept as well of slope. What if we take the slope in between 2 points like this, and this line, instead of just touching at one point, like a tangent line, this touches at 2 points. If it touches at 2 points, that's called a secant line. Oops. And we'll explore the difference between these two. What we want to mostly be able to do, as we started to do in the spring, is find the equations of tangent lines, which are the same thing as slope at a point, slope at a tangent line, instantaneous speed, all more or less synonymous. Oops.